Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm making my lesson 4 in the series of financial mathematics and exam FM preparation. In today's lesson, I'll be talking about annuities with off payments. So on the last two videos, I have shown you some basic annuities in which the periods of interest and the periods of payment are the same. So what if we have an annuity in which the periods of interest is different from the periods of payments? That is the lesson of today. So I'm going to show you two approaches to solve those kind of problem, and also I'm going to introduce the fission methods and fusion methods and some annuity traps. So now let's get started. So first of all, what is an annuity with off payments? An annuity with off payments is an annuity with payments in which are less frequent or more frequent than the interest period. For example, suppose the effective rate of interest is given at 5% per annum. An annuity with payments of 1 at the end of its 5 years period over 40 years. So here we have the periods of interest is every year, but the periods of payment is every 5 years, once in every 5 years. So that means the number of times that you make payment is less than the number of times that the interest is compounded. So this is an example of payments are less frequent than interest periods of 1 year. Now we look at the second example, example 2, more frequent. Suppose the effective rate of interest is given as 5% per annum, an annuity with payments of 1/12 at the end of its month for 10 years. So here you see we have interest is compounded once in a year, but payment is made 12 times in a year. 12 times in a year. So the number of times we make payment is more than the number of times the interest is compounded. So this is an example of payments are more frequent than the interest periods of 1 year. So the solution to annuities with off payments. There will be two general approaches for handling these type annuities. The first approaches, so here's the thing, we have two periods. One period of interest and one period of payments, and because they're not different, they're not the same, so we are going to fix one and change one. So the first solution, we are going to determine the interest rate for the payment period that is equivalent to the interest rate given in the problem. That means we fix the payment periods and we manipulate the interest rate. And the second solution, we stay with the original interest rate given in the problem and determine the payment in which the interest period that is equivalent to original series of payments. So the second solution, we fix the interest rate, but we are going to change the periods of payments. And usually the third approach is more convenient, and the reason why I'm going to show you in a couple more slides. So let's go over the first solution. First solution to annuities with off payments. So example, consider an annuity with payments of 1 at the end of every 5 years over 40 years at 5% effective. Find the present value of this annuity in terms of interest function at the effective rate for a 5-year period, less frequent payments. So this is an example of less frequent payments because the interest is compounded once in a year, here 5% effective. But the payment is made every 5 years. So like every 5 years we make only one payment. So this is a less frequent payment. So by the third approach, we are going to use a time diagram here. Here's a time diagram. At time 0, we make no payment. At time 1 here means 5 years later. Time 2 means 10 years later. So the interest over 5 years, we will call it J, because the question gives you the interest 5% per year, and here J is the effective over the periods 5 years. Is period 5 years. So we are going to change the interest rate, make connection between 5% and J, because we are going to use J's to to calculate the present value of this annuity. So let J be the effective rate for a 5-year period. Then 5 years 1 plus J should be equal to 1.5 to the fifth, because we have 5 years and each year we have 5% interest. So 1.05 times 1.05 times 1.05 times 1.05 times 1.05, totally what 1.05 to the fifth. So from here we can calculate J. So J is 1.05 to the fifth minus 1, which is 0.276. That is about 27.6%. Next, so here we already found J, the interest over the periods of 5 years. You see that here we fix the periods of payment, which is once in 5 years, and we change the periods of interest. So from the interest 5% annually, we find J, which is 27.6% every 5 years. So the present value of this annuity is just basically annuity immediate of 8 payments, in which the effective rate of interest is 27.6%. So this is the first approach. Let's look at the second example of this approach. Find the present value of an annuity immediate with annual payments of $1,500 for 8 years at a nominal rate of interest 4% compounded quarterly. So you see here, in a year we make only one payment, but in a year the interest is compounded 4 times. So that means this is in a year we have only one payment, but the interest is compounded 4 times a year. So this is an example of more frequent payments. So similar to the first problem, we also make the time diagram. So here's a time diagram. At time 1, that means 1 year later we make 1,500. Then 1 year later we have 1,500, and continue and so on. And the interest over 1 year is J. J is not given. We have to calculate J. So from 4% we are going to find J. So the effective rate over a year period is 1 plus J is equal to 1 plus 0.04 over 4, the whole thing to the 4. This is by nominal rate of interest formula. And from here we found J is 4.06%. And then the present value of 1,500 A8, 4.06%. Because this is basically an annuity immediate with 1,500 payments, 8 number of payments, and the interest over one payment periods is 4.06%. So that's the first approach. The first approach, we have to stay with the periods of payment, and we have to modify the periods of interest. Now we are going to the second approach, second solution to annuities with off payments. The second approach is basically we stay with the original interest rate given in the problem and determine the payment in its interest period that is equivalent to the original series of payments. So let's look at, we have, as I said, we have 2 type problem, the less frequent payments and the more frequent payments. So for the less frequent payments problems, the payment less frequent than the interest period, we are going to use FISSION methods. And for the more frequent payments problem, the payments are more frequent than the interest period, we are going to use FUSSION method. So let's look at the FISSION method. Example 3, determine the present value of the annuity with payments of 1 at the end of its 5 years period over 40 years at an annual effective rate of 5% in terms of interest function at 5%. So here you see that payment is made 1 at the end of its 5 years, and the interest rate is compounded every year as annual effective rate. So this is a time diagram. By the first approach, we found the effective rate over 5-year periods. But here we are going to use 5%. We're not going to find another rate, but we are going to modify the series of payments. So here you see at time 5 we make a payment. At time 10 we make another payment. At time 15 we make another payment. So the present value here, if we say v is 1.05 to -1, the present value v to the 5th plus v to the 10 plus v to the 15 plus dot to v to the 40. This is from the lesson of how to find the present value that we learned last video. So from here, use a geometric series. We have present value is the first term time with 1 minus the rate to the number of terms over 1 minus the rate. So this is 1 minus v over 40 over 1 minus v to the 5th times v to the 5th outside the parenthesis. And here we are going to flip v to the 5th to the denominator. So 1 over v to the 5th is 1 plus I to the 5th. V to the 5th over v to the 5th is 1. So here this is basically the ratio of A40, the present value of an annuity emitted of 40 payments with 5% interest effectively. And the bottom is S5. That means the accumulated value of an annuity emitted of 5 payments with 5% effective rate of interest over its year. The reason because if we divide the numerator by I and the denominator by I, we have D2. And I with I cancel, so this is how we got the final answer here. So the fission methods is applied for less frequent payments. Now we look at the fission methods applied for more frequent payments. So let's look at this example. Express the present value of an annuity emitted with monthly payments of 1/12 for 10 years at 5% effective per annum in terms of annuity function of 5%. So here the interest is compounded once in a year, but the payment is made 12 times in a year. So here's the time diagram. At time 1/12, that means 1 month later we make one payment of 1/12. 1 month later we make another payment, so total we have 2/12, and so on. So let's say v is 1.05 to the -1. The present value is 1/12 v to the 12 v to the 112 plus v to the 212 plus dot to v to the 120/12. And we have this is 1/12 v to 1/12, 1 minus v to 120/12 over 1 minus v to the 112. So this is equal to, we are going to bring 1 to the 1 over v to the 1/12 to the denominator. So 1 over v to the 1/12 is 1 plus I to 1/12, and v to the 1/12 over v to the 1/12 is 1. And remember, on the lesson of measurement of interest, I have shown you the connection between the nominal interest rate and the effective interest rate. So 12 times 1 plus I to the 112 minus 1 is basically I to the top script 12. So I to the top script 12, which is basically the nominal effective rate that compounded monthly. So this is we have a new formula. 1 minus v to the 10 over I to the top script 12 is A10 with the top script 12. This is a new notation. This notation means that we consider an annuity emitted in which we have 10 payments, and we have it lasts in 10 years, and the payment is made every month. That means 12 times in a year. So here are some results. Consider n-year annuity emitted of 1 per annum payable in m monthly installments. Then we have an to the top script m is 1 minus v to the n over I to the top script m. So this is a very new formulas. And if we divide it by I and multiply by I, we have I over I to the top script m. 1 minus v to the n over I is an. This is the present value of an annuity immediate of n payment. And this is basically at 1 top script m an, where Sn top script m is 1 plus I to the n minus 1 over I to the top script m. And this is at 1 with top script m at n, Sn. Similarly, we consider annuity due. So remember, when I talked about annuity due and annuity immediate, I stressed that annuity immediate go with I and annuity due go with D. So anything here, we are going to chain I to D. Chain I to D. And don't forget the double dots, because double dot represent for annuity due. Consider a perpetuity of 1 per annum payable in M monthly installments. This is perpetuity mean the payment is made forever. So we have here some result. Remember, the perpetuity is basically the limit of annuity. A infinity with top script m is limit n go to infinity of a n top script m, and this is 1 over I to the top script m. And similarly for the annuity due, so we have this is 1 over d to the top script m, and we find the difference between them. This is 1 over m. Next, avoiding the annuity trap. So an annuity will pay $100 at the end of every month for 10 years at an effective annual rate of interest of 5%. Express the present value of payment in terms of an annuity symbol at 5%. This is the trap because many people will got this question wrong. Many people will got this answer 100 A10 with top script 12. But this is completely wrong because 100 is made every month. So that means in a year we have totally 1200 payment, not 100. So this is wrong. The correct answer is 1200 A10 top script 12. So pay attention to this because many people got this one wrong. Many people misunderstood this one as 100 A10 to the top script 12. But remember, every month we pay 100. So in a year the total payment was is 1200. So that's what everything about this lesson. Now we are going to work on some problem. So even though the lesson is quite confusing, but I suggest you to just go by the first solution, because the second solution, the fission and the fusion methods, usually is very confusing, and they are very confusing. And when you work on the exam, the easiest way to memorize how to deal with the annuity with off payment, just go by the first approach. Let's look at this. Catherine deposited 100 into an account at the beginning of its 4-year period for 4 years. The account credits interest at an annual effective interest rate of I. The accumulated amount in the account at the end of 4 years is X, which is 5 times the accumulated amount in the account at the end of 20 years. So calculate X. So here the interest is compounded once in a year, but the payment is made once every 4 years. So this is less frequent payment problems. So the accumulated value at the end of 20 years is 100 times 1 plus I to the 20 plus 1 plus I to the 16 plus 1 plus I to the 12 plus dot to 1 plus I to the 4. Remember, because the payment is made every 4 years, so if you make the time diagram, you see that a time 0 we make a payment because this is made at the beginning. So 20 years later we need to move upward 20. So the first term is 1 plus I to the 20 and so on to 1 plus I to the 4, and this is X over over 5. So remember the geometric series. So the formula is basically we have the first term is 1 plus I to the 4, and then the rate to the number of terms. That means 1 plus I to the 4 to the 5th, because we have 5 terms. So this is 1 plus I to the 20 minus 1 over the rate minus 1. So 1 plus I to the 4, and this is equal to x over 5. Similarly, we are going to work on the accumulated amount at the end of 40 years. So at the end of 40 years, the accumulated value is 100 times 1 plus I to the 40 plus 1 plus I to the 36 plus dot dot to 1 plus I to the 4. Because the first payment is made at time 0, the second payment at time 4, then the last payment at time 36. So this is another geometric series. So apply the geometric series formula. 100 times the first term is 1 plus I to the 4. With the rate to the number of terms. So this is 1 plus I to the 4 raised to the 10, because we have 10 terms, 10 payment, minus 1 over 1 plus I to the 4 minus 1. So this is the second information. So now we are going to use these two information to solve for x. So we are going to divide side by side. So the left hand side divided by the left hand side, we have 1 plus I to the 20 minus 1 over 1 plus I to the 40 minus 1. This is equal to 1/5. And this is basically a quadratic problem. So solve this quadratic equation. We have two solutions, 1 and 4. But 1 cannot be the solution, because if 1 plus I to the 20 is 1, then I is 0. But we don't work with the case when there's no interest. So we only work with the second solution. 1 plus I to the 20 is 4. So from here we are able to find 1 plus I, and then plug into one of the two equations to find x. So x is 6,195. So the answer is E. The second problem, Jerry will make deposits of 450 at the end of each quarter for 10 years. At the end of 15 years, Jerry will use the fund to make annual payments of Y at the beginning of each year for 4 years, after which the fund is exhausted. The annual effective rate of interest is 7%. Determine why. So you see here, like at the end of every quarter, we make a payment, and we continue in 10 years. And after we make no payment at all, then wait 5 more years, we start our withdrawals. So the best way to do this one is break it into stages. So the first case, we are going to find the accumulated at the end of 10 years first. Then we are going to find the accumulated at the end of 15 years, and use it as the present value for the next withdrawals. So let J be the effective rate over a quarter, because this question, the effective rate of interest is 7%, but the payment is made by quarter, like quarterly. So we are going to use the first approach. That means we are going to calculate the effective rate over a period of payments. So let J be the effective rate over a quarter. We have 1 plus I to the 4, because a year we have 4 quarters. This is equal to 1 plus 0.07. So J here is 1.7%. Now we are going to use J to define the accumulated value at the end of 10 years. So the accumulated value at the end of 10 years, which means 40 quarters, accumulated value is 450, 840, 1.7%, which is $25,513.23. And now we are going to use this to find the accumulated value at the end of 15 years. So basically we should move it up 5 years, right? So accumulated at the end of 15 years, we use the accumulated at the end of 10 years times 1.7 to the 5th, because we move it upward, forward 3 steps. So this is the accumulated value at the end of 15 years. Now we look at the last stage. The last stage, we making withdrawals, right? We're making withdrawal annual payment of Y. I'm sorry. At the first 10 years, we make deposits, and then after 15 years we start making payments. So here 35,783.63 is y times a double dots for the rate 7%, because this is annuity due. The payment is made at the beginning of each year. And use our calculator, use a BGN mode. We are able to find y, which is 9,873. Just use the calculator and use BGN mode. Enter the number of payments for, effective rate is 7%, present value 35,783.63, and then compute the payment is 9,873. So the answer is D. Now problem number 3. A perpetuity paying 1 at the beginning of its 6 years period has a present value of 20. A second perpetuity pays X at the beginning of every 2 years, assuming the same annual effective interest rate. The two present values are equal. Determine X. So here we are given two perpetuities. The first perpetuity, we pay $1 at the beginning of every 6 months, and the payment are going to continue forever. And the present value of that perpetuity is 20. And the second perpetuity, we have the same present value, which is $20, but the payment is made once every 2 years, and the payment continue to be forever. So first, let's write down the formulas of the present value for the first perpetuity. 20 is equal to 1 plus V to the 1/12, 1/2. This is 1/2 because in a year we have two. We make payment twice. 6 years later, it's a time 1/2. So 1 plus V half plus V to the 3/2 plus dot dot, and continue forever. So this is perpetuity, and this is equal to 1 over 1 minus V to the 1/2. So from here we are able to find V, right? We have V is 0.9025. Because this is a very easy problem. First of all, we find V to the 1/2 and then square to find V. And now we continue working on the second perpetuity. So 20 is X times 1 plus V squared plus V to the 4 plus dot dot forever. Because we have X is payment, and its payment is made 1 in 2 years. So X times 1 plus V squared plus V to the 4 plus dot dot. And this is X over 1 minus V squared. So because we have found out V from the first perpetuity, so we are going to plug it in to find X. So we have X here is 3.7. So okay, so that's all for today. Thank you so much for watching, and I hope you guys enjoy my video. Next time I'm gonna continue working on some more advanced level of annuities. We still have to work on continuous annuity, increasing annuity, decreasing annuity. So thank you so much, and see you next time. Bye.